And today we study a couple of groups that are actually going to be related to the group of isometries of the hyperbolic plane, of at least two models of the hyperbolic plane, right? And these are SL2R, so 2 by 2 matrices, 2 by 2 real matrices with determinant 1, and SU11, of which I will see the definition. And so let's start by somehow comparing SL2C and SL2R. See how like kind of where they start being really actually different. Right? So first we saw, you remember we saw, I mean, we know that this is isomorphic to the Möbius group, right? I mean, we had a group homomorphism from GL to C to the group of Möbius transformations that to each matrix associates its corresponding Möbius transformation, right? And then we saw this group homomorphism is surjective, pretty much by definition of what a Möbius transformation is, and we saw that its kernel, the kernel of this homomorphism, was precisely the non-zero multiples of the identity, right? That is, we saw that two matrices give me the same Möbius transformation precisely when one is a non-zero multiple of the other. So this is this is really isomorphic to the Möbius group. So it's kind of the Möbius group disguised in a way. And this I'm going to be. So let me choose another color. Right. So this is PSL2C. Okay, like by definition. Right, and then we saw that actually any Möbius transformation can be realized as the Möbius transformation of a matrix with determinant 1, right? And so somehow that's what it means, that this inclusion induces an isomorphism here, right? So this is also isomorphic to MÖB-C, to MÖB-C bar, sorry. Yeah, and then this I'm going to sorry, here I should have written, sorry, here I should have written PGL2. I mean, for this G, right? Okay, and then here I write PSL2C, right? Somehow, conceptually, what I'm doing is I'm in each group, I'm modding out by its center. So the notation really is, I take the group and then I just take P, take the group P. Okay, so that's the projective special inner group, the projective general inner group, and these are really kind of the same group. Right? These are isomorphic with the isomorphism induced just by the inclusion. Okay, so these are essentially the same group. Right now, in the real case, again, the inclusion now of SL2R, so those the real 2 by 2 matrices with determinant 1, right, into just the group of all invertible 2 by 2 real matrices, of course induces a homomorphism, simply because, of course, this plus and minus the identity, of course, are multiples of the identity. So there is this well-defined group homomorphism. Here again, this is actually PSL2R, just by definition, and this is PGL2R. Right, and this one one can see that it's actually still injective. This I leave as an exercise. So this is still an injective group homomorphism, but it is not surjective. Right? I mean, just take you see, like take this matrix which has determinant 1 is what is a 4 minus 2 is not in the image, right? I mean, and the point is right, somehow the point is, at least when one, if you want to see it kind of through Möbius transformation, somehow the point is, if you have your invertible real 2 by 2 matrix, when you want to get a matrix with determinant 1 giving you that Möbius transformation, you have to divide by the square root of the determinant. But it is of course possible that the determinant is negative, so in the end the matrix that does the job is actually not real. That's really kind of the problem. So here we can see already kind of a significant difference between these two. Here, of course, instead of non-isomorphic, I should really say, that more correctly, that this homomorphism, which is injective, is not an isomorphism. Right? But anyway, I will just write it kind of like this, which is more vague, because this is more vague. It's actually a different statement, right? Because now I'm asserting actually that it's impossible for them to be isomorphic, whereas first I was just interested in saying that this is not an isomorphism. But anyway, I will leave it like that. So in this case, PSL2R actually only sits as a subgroup here, and the exercise is compute the index. This is not a hard exercise. Right. Okay, now, kind of for future reference, you see somehow here in this slide, I am somehow already getting ahead of myself. I'm already thinking that the upper half plane is going to be a model of the hyperbolic plane. And I already know that I'm going to be interested in computing the group, the isometry group of that model. And because of that, and because somehow I already know that it's going to be given in terms of Möbius transformations, kind of I get ahead of myself, and then what I want to do is to characterize those 2 by 2 complex matrices of determinant 1 that have the property of leaving the upper half plane bijectively invariant. When I say bijectively invariant, is that not only one has this, right? One actually has equality, right? Because it is perfectly possible that one can have something like this, but not equality. Right? Think for example of vertical translations. Right? I mean, a vertical translation upwards, it preserves this set, right? But not bijectively. Okay, and so in this theorem, we characterize those complex 2 by 2 matrices of determinant 1 that leave the upper half plane bijectively invariant as follows. So these are precisely the 2 by 2 real matrices of determinant 1. So that's kind of the main point. Yeah, and then here are like these are kind of just auxiliary steps into proving that it's equivalent for a matrix to be in SL2R and for its Möbius transformation to leave the upper half plane bijectively invariant. So let's prove this theorem. So for A in SL2R, we want to show that it sends the upper half plane into the upper half plane, and R bar, which is R union infinity, into itself. So one thing is clear, right? If one is in SL2R, for a matrix in SL2R, when one analyzes this expression, and then one inputs a real number, for instance, well, it's clear that this is going to be either a real number or infinity. If the matrix is in SL2R. And it's also clear that when I plug in infinity here, what I obtain is either a real number or infinity. So for A and SL2R, this is clear. Okay, and now to show the other statement, you see, by now I already know that the Möbius transformation sends R bar to itself, and I know that the Möbius transformation is is a homeomorphism of C bar, right? And this and R bar splits C bar into two, right? Into two disks. So because of continuity and because it's a homeomorphism and because because it's a homeomorphism, you see either it sends the upper half plane to itself or to the other one, right? And also, you see, it's enough to take a point and see where it lands. If it lands here, I know that the image has to be the whole upper half plane. And if it lands down underneath R bar, below R bar, then I know that the image has to be kind of the lower half plane. So it's enough to consider I, which lies in U, and to check that the image is in U. But you see, but then when one does this computation, so one takes mu A of I, and then you see one does this kind of this usual trick, right? Kind of to divide by this complex number. Kind of one just multiplies with it multiplies and divides by its conjugate. Right? So yeah, and remember that the entries are real. I'm assuming that the entries are real, and then one can I just perform this product because you see that the imaginary part has to be what alpha delta, right, minus gamma beta, right, divided by this, right. But then you see alpha delta minus beta gamma is the determinant of A, which is 1. So this is 1 divided by gamma squared plus delta squared. It's positive. So this is indeed the case. So by continuity, this is indeed the case. Okay. Let's go to 2 implies 3. Right. So that if it sends U to inside itself and R bar inside itself, then it preserves U bar bijectively, and of course U bar is the topological closure of U in C bar. So really U bar is really U union R bar. So if you if you want here. and I would say that the argument is again more or less simple. I mean, this is a circle in C bar, this is a circle in C bar. So if this is contained in this, they are automatically equal, right? It's kind of one circle contained in another. So they really have to be the same circle. And then again, then once I know this, then you see, I know also this by assumption, and then nothing from outside U union R bar can enter U bar, because otherwise, you see, I mean, I have, if you want, I have R bar, I have U. I know that this and this are equal, right? And I know this by assumption. So if there were some point outside U union R bar that by the Möbius transformation gets inside, so let's say I don't know, Z and mu A of Z. Right. I cannot get inside, so let me think. Yeah, it should be the same argument. Why am I not saying it? Right. I mean, yeah, it's the same argument. Sorry. I mean, it's the same argument as the one I used before, because I know that mu A is a homeomorphism, and I already know that it sends R bar precisely in R bar. This I already know. So the the two connected components of the complement of R bar have to be sent correspondingly to the two connected components of R bar and C bar. And then it has to be the case that then either one has this, like a connected component goes entirely to itself, or the other way around. Right? So if one already has this, if U goes to itself, then nothing outside U can go there, because then the whole component, which is minus U, would go to U. You see? So somehow the two components their image would be really contained in just one component. But then the inverse would separate. You see, the inverse then would separate this one component into two. So this contradicts continuity. So it really is the same argument as before, and then one really has equality here, so one has equality. Right, and then let's go with 3 implies 4. And so then things become kind of just general topology. I mean, because U is the topological interior of U bar. If you think about it, that's obvious. I mean, that's this kind of, this corresponds to taking the open disk, which is the interior of this closed disk, if you want, where I'm talking about disks in C bar. Right? Okay, but then a homeomorphism sends precisely interior to interior, right? I mean, for a homeomorphism, it is the same to take interior before or after, right? And now using this assumption, this would be equal to U bar, right? And then I have this interior outside, right? But this interior is, as we said, U itself. So I have the equality between this and this, right? So, and this really was kind of more like just abstract topology. And finally, you see, now I know that if A is in SL2R, then U goes to U bijectively, and now I finally want to go back and then take a matrix, a complex 2x2 matrix with determinant 1, which preserves U bijectively, and then I want to show that its entries are actually all real. That's what I want to see. So if this happens, then pretty much by continuity, kind of by abstract considerations, R bar has to go bijectively to R bar. Well, simply because R bar is precisely the boundary of U in C bar. Right. And mu A is a self-homeomorphism of C bar. So all of this, what it really says is that the boundary goes to the boundary bijectively. Okay, so now I know that, and you see, knowing this, now once I know this, I'm going to use this knowledge to argue about the entries of A, because then I can start plugging in real numbers and start deducing that certain expressions involving the entries of A are real numbers or infinity. Right? So, right. So I take the complex the conjugate of my matrix A. So this is just the conjugate, and so you see, for every time I'm in R bar, what I realize is the following: mu b of z is alpha conjugate z plus beta conjugate divided by gamma conjugate z plus delta conjugate. But you see, conjugation, it really respects sums, products, and quotients of complex numbers. This is simply the conjugate of alpha z plus beta divided by gamma z plus delta, the conjugate of the whole thing. Right? And this is the conjugate of mu a of z. Right? So this is what I'm asserting here, and that is simply just because complex conjugation opens sums and products of complex numbers. Right, but you see, I took z in R bar, and R bar is really, and so I know that this is in R bar, and R bar is really closed under conjugation. So what I obtain is that this is really just mu a of z. Right? I mean, because the conjugate of any point in R bar is itself. That's the point, right? The conjugate of any point in R bar is itself. Okay, so what do I realize? What I realize is for points in R bar, their image under B is precisely their image under A. So these two Möbius transformations, mu A and mu B, they coincide all along the R bar. So they coincide on at least 3 points. So they are the same Möbius transformation. And since they are the same Möbius transformation and both of them have determinant 1, one is plus or minus the other at the level of matrices. Okay, what do I want? What I would want is actually that A is equal to B, because then alpha is equal to alpha conjugate, and so a real number. Beta is equal to beta conjugate, and so a real number, etc. So what I really want here is that A be equal to B. So I want to discard the other option. Right? So I'm going to discard it. What happens if the option I don't want happens? Well, then you see, then all these real parts are 0. Right? The real, because alpha would be minus alpha conjugate. So from there you can deduce that 2 times the real part of alpha is 0. So the real part of alpha is 0, etc. And the same for the others. So those real parts are all 0, which means that alpha itself is just a real multiple of I, and so are the others. Right? And then what do? I evaluate at I, because you see, what I know is that on their mu a, I goes to something with a positive imaginary part. Okay, so I plug in I, right, and I just perform the computation. Here again, kind of you see what I have here is this is minus c, really. So this this is minus c, and then let me see. This is minus c plus id, and then I divide this. Sorry, yeah. So I plug in I, right? So I mean this is alpha, this is alpha, this is beta, this is gamma, this is delta. I plug in I, and then I can factor one I and cancel it, right? So I can cancel this, and this. And so I get AI plus B divided by CI plus D. And then I compute this quotient by, again, the trick of multiplying and dividing by the conjugate of the denominator. And so this is why here I have, you see, D minus CI, right? Whose imaginary part is AD minus CB, AD minus CB, which, since this is in U, is positive. So this imaginary part is positive. Okay, that's positive, but then I go back, right? 1 is the determinant of A. The entries of A, well, I just substitute, and I compute the determinant, right? So what I get is, you see, I times I is minus, right? So this minus, this I square goes out as a minus, and then I got ADCB, right? And I know this is positive, so this is negative. So 1 is negative. So what must be wrong? This assumption must be wrong. So A must be equal to B, and I'm done, right? Okay, so this characterizes the 2 by 2 complex matrices of determinant 1 that leave the upper half plane bijectively invariant. Fortunately, the answer, the characterization, is given in simple terms, right? I mean, the matrices, they are not strange matrices, right? They are just real matrices with determinant 1. This is not a strange set. It's not a strange group. Now, you see, now consider 3 points in R bar. Okay, let's say 0, 1, and infinity, right? Which you see, 0, 1, and infinity, they are actually clockwise, counterclockwise. Sorry, right? They are counterclockwise. Right, and so and now take 3 distinct points. You see, ordered in the counterclockwisely in the unit circle, right? And so my 3 points, 0, 1, and infinity, can be sent to these 3 points in the circle, right? So if you want 0, 1, infinity, these are counterclockwise oriented. Now take 3 points in the unit circle, counterclockwise, let's say first one, second one, and third one, for instance. And what I know is that there exists exactly one Möbius transformation sending 0 here, 1 here, and infinity here. What can I immediately deduce? That the whole R bar goes bijectively to this circle, and that since here my 3 points are also kind of oriented in the counterclockwise sense, I know that the upper half plane goes here. So in other words, what I have just pretty much done is, given two disks in C bar, I've told you pretty much all the possible ways of mapping one to the other with a Möbius transformation. Okay, but then this means that it really, since here I have this choice is arbitrary, then the second choice is arbitrary, and then the third choice is arbitrary, as long as in the end I have this. For sure, there are going to be many Möbius transformations sending U bijectively to the unit disk. Right. Right. So this is true. Right, and I'm going to use. I'm going to. So let me think. I mean, I'm going to use this to show that the subgroup of SL2C consisting of the matrices whose Möbius transformation sends the unit disk bijectively onto itself is a subgroup of SL2C conjugate in SL2C to SL2R. And the conjugating Möbius transformation can be any Möbius transformation sending 0, 1, and infinity to my 3 points. That's what I'm going to do. And I'm going to compute that subgroup, the group of matrices whose Möbius transformation preserves the unit disk bijectively explicitly, kind of just as before, as I just did. The subgroup of A's with this property, of the matrices A's with this property, is precisely this concrete group. I'm going to do the same, but now for the disk. Why? Because I'm already getting ahead of myself, and I already know that the disk is going to be a model for the hyperbolic plane, and I know that the isometries are going to be related or given by the Möbius transformations of C bar that preserves the disk bijectively. So it's because I already know that I know what's coming. So I'm just going to compute the subgroup now, right? So that later I can just use it directly. So consider this matrix, right? So it's almost the identity, right? But it's not quite the identity. And then define SU11 to be the subgroup of GL2C consisting of the matrices with the property that when I perform this sort of conjugation, but it's not quite conjugation because here it's not A inverse, but actually this other matrix. But anyway, when I multiply this matrix with A and with this other matrix, I get this matrix, right? So it's kind of all those A's that leave this matrix invariant under these operations. And this matrix is the one that appears in kind of when one studies complex vector spaces with Hermitian form, right? So it's kind of the conjugate transpose. So I transpose and I conjugate, right? So just Um, okay, and so somehow the point is, if you have already seen some course on Lie groups, that's a common way of defining a matrix Lie group, right? By kind of as a group, as a certain group of matrices so that with certain operation leaves certain matrix invariant. So somehow what I just did was define this group as a matrix Lie group, and then the first lemma is to try to give, a description of the entries of a description of the group, or a description of how the entries of any of the elements of the group look like. So the lemma, what the lemma asserts is that really SU11 really consists of the following matrices. You see, is determined by the matrices with determined by picking any two complex numbers, alpha and beta, with this property. So you see, it's kind of instead of kind of having this one has minus, so it's kind of this already starts looking like something hyperbolic, but anyway. And then you see, whenever one has a pair of complex numbers satisfying this identity, these two entries are just here the conjugate of this one, here the conjugate of this one. Right. So an explicit description of the elements of this group. So if I have this lemma, I mean, there is one inclusion that kind of should be easy, right? Because if I already have this explicit description, I mean, these explicit elements, for these explicit elements, I can just perform these operations and then see what happens, right? But that's I would say very mechanical, right? So I would say that this is obvious. I mean, this just do it, right? And really the inclusion that really is kind of more interesting is the other one, right? Or more challenging is the other inclusion. So take any matrix in GL2C satisfying this, right? So the first thing is that yeah, let me see. Yeah, the first thing I want to argue is that the determinant is 1. So I'm going to look at this equality. And from this equality, what I obtain is that here is determinant of A minus 1. And this one is the conjugate of the determinant of A. Right, and this is minus 1. Right, so the minus 1's cancel. So I get so I really get that the norm of the determinant is 1. yeah, which tells me that I made a mistake. I should just restrict my attention to those of determinant 1, because otherwise I get stuck here, right? Yeah, so I really define SU11, restricting the attention to SL2C. Okay, well, in that case, then this is actually obvious, right? And then I don't have this problem of not being able to deduce that the determinant is 1. Okay, and then the equality defining the group here, right? Just written the other way around. Okay, and then I perform this computation explicitly, and what I obtain is this. So what we deduce immediately is that this is equal to 1, so this is here, and that this is equal to minus 1, right? So this is here. So you see, norm of gamma minus norm of delta, so equal to minus 1, so this already changed, right? Okay. Now, okay, and I know that this is 0, and that's here. And this other entry is actually the conjugate of this one. So it's kind of kind of. I also know that this one is 0, but somehow if I write this down, that's just the same equality. or if you want, it's just redundant with this one. And from here, well, you know, this when I subtract this, I still have 1. So this one is at least 1, because this is positive. Right? So this is not 0. Same thing here. To this non-negative, I subtract something non-negative, and I still have 1. So this has to be still at least 1. Right? So this is not 0. And now I know I use this, that this is not 0, to in this equality just solve for beta, right? Because here then I can just you see, pass this one to the right and divide by delta conjugate. Okay, and then from where is it? Right. So now I use this equality of the determinant, and here I plug in beta. I substitute this beta. So I substitute, and I know that it gives me 1. Right. But then you see here I can multiply with then I have this equality, and I can multiply with the conjugate delta. So conjugate delta passes to the right, and here it becomes the norm square, right? And then this gamma conjugate becomes norm square of gamma. I can factor alpha. And then you see here this is 1. So this is 1. So this is actually just alpha. And what I obtain is that delta conjugate is just alpha, which is something I wanted, right? Because from here I want to arrive at this one is conjugate of this one. Okay, so that's one desired thing. And then for the other one, well, now I know that these two are equal. and I recall this other equality, and you see here alpha is equal to delta bar, so I have beta equal to gamma bar, to gamma conjugate. Okay, so now I have the desired form of this one. It has the desired form, and the determinant is 1, but the determinant is precisely the norm of alpha square minus the norm of beta square. So my matrix was indeed in the desired set. Right, but of course here kind of with this kind of to realize that one restricts the attention only to the matrices in SL2C, kind of just I should have known, right? Because that's exactly what I did before for the other case. So I'm kind of I really should have known, but anyway. Okay. As I said, I mean, I pretty much already introduced a set that is going to be one of the models of hyperbolic geometry. Another model is going to be the Poincare disk, so I introduce it now. And now what I'm going to do is to take a specific Möbius transformation, sending, as I said before, 0, 1, infinity to certain 3 points in the unit disk. And now what I'm going to do now is to show that at the level of matrices, the corresponding matrix of this Möbius transformation that I'm about to exhibit conjugates SL2R and SU11. So so I'm going to give an explicit matrix that conjugates them. Okay, so they are in particular going to be isomorphic and homeomorphic. Right? I mean, they are going to be actually isomorphic as Lie groups. And what I do is, okay, and then, I mean, I pick these 3 points, right? But there is something which is, I'm not going to send 0, 1, and infinity, but actually minus 1, 0, and 1. Right? So minus 1, 0, 1 in that order. It's still counterclockwise, and I consider the points I minus 1, but then I want to do it counterclockwise. So let's say that I start here and counterclockwise this and this. So I'm going to consider the Möbius transformation sending minus 1 to I, so that's here, 0 to minus 1, that's here, and 1 to minus I, that's here. How can I compute actually such a matrix? Well, what I know is I know how to send this to 0, 1, infinity, and I know how to send this to 0, 1, infinity, right? And then I compute one followed by the inverse of the other, right? And that way I come up with an actual matrix, right? And then okay, I did all of that at home, and then I arrived at this matrix. Okay. Right, and then, well, if I just give you this matrix, then checking that it has the correct behavior, it's just a matter of analyzing this formula, right? And then just plugging in these 3 numbers, right? So that's easy. So it's kind of just do it, right? I mean, by the way, this is often called the Cayley transformation, the Cayley-Möbius transformation. And what I know is that, well, it takes, as before, it sends R bar to this, because I know it sends circles to circles. And because here I have counterclockwise oriented, and here I have counterclockwise oriented, it sends U bijectively onto the Poincare disk. And I know that Möbius transformations are biholomorphisms. So the Cayley transformation is actually a biholomorphism from the upper half plane to the Poincaré disk. Now, one nice point is that once I know one matrix whose Möbius transformation sends what I want bijectively onto what I want, then I know all matrices. That's what this exercise says. Right? It says precisely those of the form. And here there's an easy part of the exercise. You see, if I take anything in SL2R and I follow it with this one, I know that this is going to be mu of 1 minus I, 1I, preceded by mu of A. And I know that this preserves U bijectively. So at least I know that all those Möbius transformations of this form send U to D bijectively. Okay? And then the exercise is, okay, any one such is of that form. That's actually the exercise. Okay? Okay, which is very nice, right? I mean, it reduces knowing all possible matrices to just having computed one. Okay, and then the Promise Theorem, which is, I mean, I know that the Cayley transformation sends U to D bijectively. So I know that the subgroup of not C bar consisting of the Möbius transformations that preserve U bijectively and the group of mob C bar consisting of the Möbius transformations that preserve D bijectively, those two subgroups are conjugate in mob C bar. What the theorem says is that we know not only that, we know that even before taking Möbius transformations, just at the level of matrices, they are already conjugate. Okay, so somehow this theorem is kind of stronger than what one can immediately deduce. Okay. Now, for the proof really becomes just matrix computations, but for the proof, you see this matrix, the matrix precisely giving rise to the Cayley transformation. It of course doesn't have determinant 1, so it doesn't live in SL2C, right? But the first thing to notice is that even though it doesn't live in SL2C, if one shows this equality, then this one and this one are conjugate in SL2C. Right? And it's simply because if this is the case, then of course I can replace this one by the same thing divided by its the square root of its determinant, right? And then substituting this by the inverse of what I just said, this one divided by the square root of its determinant. And you see the square root of the determinant here is and whatever here, they are just going to cancel. And I'm really going to get this. And if this is true, then they are conjugate in SL2C, even though this one doesn't live in SL2C. Okay, now checking that this one, checking this equality, really, it really is just using using the description of the explicit description of the entries of the elements of SU11 and just matrix multiplication. Right? So somehow what one does is, first of all, one computes the inverse, right? And then one takes an arbitrary matrix in SL2R, one conjugates, right? And then when for this conjugation, then I replace this with 1/2 this, right? So that's the 1/2 here, right? And then I just start multiplying, blah blah blah, and then I look at what I arrive, and somehow I just organize it in such a way that here it becomes clear that, for instance, this and this are conjugate, right? So it's alpha plus delta plus I this. Here's alpha plus delta plus I minus this, right? So indeed, these two are conjugate because I started with a matrix with real entries. Similarly, this one and this one are conjugate, alpha minus delta plus I this, alpha minus delta plus I minus this. And one computes the determinant. Right? So, and that actually, I don't have to compute the determinant, right? Because the determinant of this is going to be just the determinant of this. And this one I know it has determinant 1. So you see, so it's really just matrix multiplication, and then I just use the explicit description of the elements of SU11. And conversely, right? I mean, I take something in SU11 already described nicely, right? And I already with determinant 1, and then I conjugate, but of course, kind of with the inverse, right? I mean, now the inverse appears on the left, of course, and this one on the right. But otherwise, it's just matrix multiplications, and then what I obtain here is, you see, this plus its conjugate, real number. This plus its conjugate, it's a real number. This plus its conjugate is a real number. This plus its conjugate is a real number. Right? So, right, and then the determinant was always 1. Right? When I conjugated here, the determinant remains 1. So the result is in SL2R. Okay, so they are conjugate subgroups, and this is something very nice, because you see, SU11 seems to be a little more kind of mysterious than SL2R. I mean, somehow, at least I personally find it a little bit bothering. You see that one has to keep track of this equality and keep track of having here conjugates of these ones. So I don't know. I tend to think that this seems to be more mysterious, but up to conjugating with a very explicit matrix, it's essentially SL2R, right? But not quite what you just said. So what I said was, the Möbius transformations that preserve this bijectively form a subgroup conjugate to the Möbius transformations that preserve this bijectively. So preserving U bijectively, like U onto itself bijectively, those are conjugate to preserving D bijectively.
And the conjugation then is always the Cayley transformation.
Right. The Cayley transformation works. The Cayley transformation does the job, like it conjugates. But actually, any Möbius transformation sending U to D bijectively does the job. Right. Right. And now, is it clear that once we have this, is it clear that once we have this, the fact that those two subgroups, the one that those two subgroups of mob C bar, the one, and namely the ones that preserve this bijectively and the ones that preserve this bijectively, they are conjugate subgroups? Yes. Okay. Okay, and now, right. So one nice thing about this is that they are kind of pretty much the same group, just disguised. right, and so one arrives at a similar characterization now of those 2 by 2 complex matrices with determinant 1 that leave whose Möbius transformation leaves the disk bijectively invariant. Those are precisely the matrices in SU11. I leave the proof as an exercise. The proof somehow is by now can be done in a way more direct way than what I did for in the case of PSL2R, because now we know that SL2R and SU11 are conjugate, so one can use that to produce a kind of a shorter proof of this theorem. Right? So that's why I leave it as an exercise. Okay, and now let me show you a picture of SU11 and hence also of SL2R. So somehow the theorem in order to be able to draw SU11 is this theorem, which is that it is just a solid torus disguised. Right? Okay, and you see, I mean, and here there are 2 things. How does one realize this? Right? I mean, how does one realize that? That I don't know. Right? I mean, because I didn't realize it by myself. I actually read it in a set of notes by Siegel. It's some lecture notes on Lie groups, if I'm not mistaken. And it's it's some book by the London Mathematical Society where it's 3 sets of notes, one by Siegel, another one by MacDonald, and another one by Carter. And then in these notes he just mentions this, right? So okay, so how did he see it, or I don't know. Hence, I also don't know, like okay, how do you come up with the formula that actually does the job? I also don't know, right? I mean, I saw the formula in his notes. Right, but okay, but once you know the formulas, then kind of you can just make the obvious observations, right? For instance, if you are here in SU11, well, of course, this one lives in the disk, right? And then because of this condition that norm alpha square minus norm beta square is 1, that this number actually kind of lives in the disk. And also knowing the formulas, one can just check, they are mutually inverse. Okay, so I just leave it as an exercise that they are mutually inverse and they are of class C infinity. Okay, so kind of this proves the theorem, but I didn't really give any good insight as to how you come up with such an observation, right? Well, unfortunately, I don't know how one come up with such a thing, but I do know how one can use these formulas to draw a picture of SU11, but more importantly, to draw a picture in such a way that one can see where the matrices that gives you parabolics live, where the matrices that give you elliptic transformations live, and where the matrices that give you hyperbolic transformations live. By now, we should be able already to observe that if you give me a loxodromic Möbius transformation, it never preserves a disk. And by this, I really mean if you give me a loxodromic Möbius transformation, let's say nu, and you give me any disk in C bar, the nu of the disk is never equal to that same disk. Why? Well, by now it's kind of okay. It should suffice to check the standard examples, and for the standard examples, can you just check it, right? I mean, there really isn't multiplying by a complex number alpha and not lying in the circle and not lying in the non-negative real numbers. Multiplying with alpha doesn't preserve any disk whatsoever, right? And so when you consider an arbitrary loxodromic Möbius transformation, it has the same property of not preserving. So this means that if I take a matrix whose associated Möbius transformation preserves the Poincare disk, I know that the Möbius transformation is not loxodromic. In other words, by now we know that in SU11, one doesn't have loxodromic elements, and also in SL2R, because the elements of SL2R preserve a disk, and the elements of SU11 preserve a disk, and loxodromic ones, they don't. Okay, this will come up in a few moments. Right, so by the way, here it should be W. Right, so for a point in the torus, right? So for a point in the torus with this psi pass through SU11, so we have this 2 by 2 matrix. So we can take its Möbius trace, right? Because I mean it's a 2 by 2 matrix, right? So it has an associated Möbius transformation and so on. Okay, and the trace I compute it in terms of this one. This one already has determinant 1, so the trace is just this plus this square. So it's here, and you see this conjugate comes from this one here, and then kind of I just simplify. So for instance here the trace is exactly equal to 4. Let me write it with some other. This is exactly equal to 4 if and only if, well, this is exactly equal to 4, right? But that is this is exactly equal to 4. But if this is exactly equal to 4 is equivalent to this part being equal exactly to 1, and this being exactly equal to 1 is equivalent to just this being equal to this. So, all right, but these two quantities being equal is equivalent to this just being equal, right? I mean, I just passed this to the other side. Okay, and now I'm out of time, so let me wrap up. So you see here, this looks like the equality of the identity for a sphere, because this Z lives in the disk. Right? Now at W, so you see, think only about W. Right? So think about the complex plane and the unit circle. Right? I mean, W lives in the unit circle. Right? So I can think of taking this real part as kind of this. I can think of this as being at the kind of as being this segment of the circle, but deformed. Right? If I think that way, you see, I have to consider 2 times this. So it's like I have to consider 2 times this this interval, the interval minus 1, 1. So I take it and I'm going to consider it twice, right? And I have to undeform it twice. One going up to obtain this, and one going down to obtain this. So I'm going to keep that in mind for the very end, because now if I think of the 3-dimensional space Z with W, well, not with W, but with the real part of W, this is the equation of a sphere. So here you see I have the disk where Z lives, and I have the real part of W. This gives me the white sphere, right? But that's the white sphere in which I use the real part. So I have to go back to actually take the circle, right? So this one I have to kind of undeform it onto this half part of this, where I really have a torus, but of course I couldn't draw all the circles, right? But so I really have a half torus here. Oops, yeah. And inside that half, then the picture of this sphere kind of becomes this sort of sausage-like. Do you see it? I mean, this becomes this becomes this, and then I have to really undeform, right? So the sphere deforms, and I have to do that for this side, but also for this side. So for this side as well, right? And the surface of the sphere represents those points where I have parabolics, because I have this if and only if I have a parabolic. So in this three-dimensional torus, the kind of the white, the union of the two white, kind of the skins of the two sausages, that's the matrices that give me parabolic. Now, when do I get elliptic? Here, here, here. So the elliptic ones live inside the sausages, but not in the skin, right? And when do I have hyperbolic? Here, here, here. If I didn't screw up. I think it's correct. Yes, I think it's okay. I mean, okay. Maybe let me retract and finish that analysis the next time, kind of to do it to not rush through the analysis, but at least we know, right, that those that you are seeing in white are the parabolics. And let me just show you a final picture. Yeah. So that's, you see that those are the parabolics in the solid torus. Okay. So those are the parabolics. Right, and that's the torus. But then as I said, by analyzing what happens in the by analyzing what happens in with these inequalities, I'm going to deduce some inequality here, and then I'm going to see that being a hyperbolic or elliptic corresponds to being inside or outside the white sausages. Okay, but this I finish the next time. Okay, and so I ran out of time. So some homework to hand in to prove that SL2C is path connected but not compact. I would say it's a very beautiful exercise, especially this path connectedness. And yeah, and then also I want you to start reading something. This is not very hard to read, and it will give you an insight of what we're going to see starting next week with the several models of the hyperbolic plane. And all right, see you next Monday.